Hello, Mr. Betts here. So I want to look at a few examples where we are going to try to apply the mean value theorem. And if we can, then we're going to solve for values of C that meet the conditions of the mean value theorem. So the first thing we want to do is we want to figure out if the mean value theorem even applies. So there's two conditions that have to be met for the mean value theorem to apply. One is that the function has to be continuous on the open interval from the starting point to the ending point, and it has to be differentiable on the closed interval. So there are certain functions that we deal with that we just know that they're continuous and we know that they're differentiable. We can find points of discontinuity by looking for where, for example, a derivative is equal to zero, a denominator is equal to zero, where we might have a piecewise function and at the boundary between two of the pieces, they might not match up and it's not continuous. But in general, we have some functions that we know are always going to be continuous and always differentiable, and one of those is polynomials. So a polynomial, we can take the derivative of it, we can plug in any x value we want, so it's continuous and it's differentiable. So the conditions are met. We do want to, if the conditions are met, we want to say that. So we'll just say it's pretty simple here. F of x is continuous and differentiable. DIFF is a good enough abbreviation for differentiable on the interval. And I'm going to just include the endpoints for both because if the endpoints are included, then that's more than enough for showing the interval we need for differentiability. So since it's continuous and differentiable on this closed interval, then we know the mean value theorem applies. And what the mean value theorem then says is that if we find the slope of the line through the two endpoints, which is going to be f of 2 minus f of negative 1 over 2 minus negative 1, that's going to be the average rate of change, and that has to equal at least 1 point the derivative of f evaluated at some point c, where c is somewhere between a and b. All right, so what I'm going to do is I'm going to take the derivative here. I'm going to jot it down in here. F prime of x is equal to 3x squared, and plug that in. So we got c in there. We're going to have 3c squared is equal to f of 2 is going to be 7 minus f of negative 1 is going to be negative 2 over 2 minus negative 1 is 3. So we have 9 over 3, which is 3. So we have 3c squared equals 3. And just doing a little algebra here, we're going to end up with c equals plus or minus 1. Now, not quite done, because the mean value theorem guarantees points, or a point at least, on the interval from negative 1 to 2. But remember, the guarantee is only on the open interval. So that's mentioned here in the problem, which means that I want to throw out any values that I got here for C that are not on that open interval. And it turns out that we got a value at negative 1 that is not on the open interval from negative 1 to 2. So we are going to throw that out, and our final answer is just C equals 1. All right, and what that means is if we were to graph this function and we were to draw the line that goes through the two endpoints at negative 1 and at 2, then the slope of that line is going to be parallel to the slope of the line tangent to the curve at x equals 1. Second one here, this is an example of a function where we might have some trouble with differentiability. This is going to be continuous because x squared minus 1 is continuous, and the only thing the absolute value does is it takes negative values and makes them positive. So we're not going to make a continuous function discontinuous by making an absolute value, but we might have a problem with differentiability because we might end up with a corner or a cusp somewhere. So I'm going to think of this just kind of informally as the graph. If we were to graph the function y equals x squared minus 1, it's going to look like this. And the absolute value is going to take the part that's below the x-axis and flip it, reflect it over the x-axis and put it above. So this graph is going to look like this. And just knowing some things about this function, I do know that the point here is going to be at x equals 1. Sorry, that's supposed to be a 1. And so at that point, the derivative is not going to exist because of the cusp there, which means that the mean value theorem does not apply. All right, so I'm going to say the mean value theorem does not apply, but I also want to state why not. Well, the reason the mean value theorem is not going to work is because we have a point on the interval from 0 to 2 where the function is not differentiable. So to answer this, I'm going to say the mean value theorem does not apply because f of x is not differentiable at x equals 1, which is on the interval from 0 to 2. And notice that I put the open interval because that's the interval that we're looking at for differentiability. I do want to point out that had this interval been a different one, say the interval was from, instead of 0 to 2, let's say it was from 1 to 2, this would actually be okay. So even though the function's not differentiable at 1, if we're looking just at the open interval, we don't have to include 1. So the mean value theorem would work if we were looking at a different interval, specifically in this case, the interval from 1 to 2. So as long as the interval doesn't include in its interior 1 or negative 1, then the mean value theorem can still work on this particular function. I do also want to refresh real quick how we can analytically take the derivative of something like this. Remember, the absolute value of x squared minus 1 can be written as a piecewise function as x squared minus 1 as long as that is positive or equal to 0, and the opposite of x squared minus 1 if the inside of the absolute value is negative. And so what we can do here is rewrite these inequalities. So this is going to equal x squared minus 1 for values of x less than or equal to negative 1 or greater than, didn't give myself enough room here, or x greater than or equal to positive 1. And then it's going to equal 1 minus x squared for values between negative 1 and positive 1. So once we do that, we can take the derivative of each piece and look at the derivative at the boundaries and see if the derivatives are approaching the same thing. Because remember, derivatives are defined as limits, and so for the derivative to exist, the limit has to be the same on both sides, or the derivative has to be the same on both sides. All right, moving on to the last example, we have a piecewise function. So I'm going to get to talk about how we take derivatives of piecewise functions here. I know that sounds exciting, right? So the derivative of f, I guess I should probably check continuity first. So let's make sure this function's continuous. And the only place we're going to have trouble with continuity is at x equals 2. All right, so remember, for a mean value theorem to apply, it has to be continuous and differentiable on the interval. Continuity has to include the endpoints, differentiability does not. Notice that the boundary here is in between 1 and 3, so that's the only point of concern here. So I want to look at the limit as x approaches 2 from the left of f of x, and for that we're looking at this branch right here. So we plug 2 in there and we get 4 plus 16, which is 20. And then I want to look at the limit as x approaches 2 from the right of f of x, and that's going to be 8 plus 12, which is 20. All right, so this confirms that since the function is approaching the same value from both sides, and indeed f of 2 is equal to, we're using this branch for that also, is also equal to 20. This is the definition of continuity. So we need to check the limit on each side. We need to check the value of the function, make sure those all match up. All right, so the function is continuous at 2. It's also continuous anywhere to the left of 2 and anywhere to the right of 2 because they're just polynomial functions. What we need to check next is differentiability. So let's take the derivative. And the derivative is going to be a piecewise function itself. So 2x plus 8 For the top branch, 3x squared. For the bottom branch, this is going to be when x is less than 2. This is going to be when x is greater than 2. And remember, we're not going to include the equal here unless these are approaching the same thing from both sides. So we do the same thing we did checking for continuity, but we're doing it with the derivative. So as we approach 2 from the left, I'm going to do this one a little less formally. So if we plug 2 in here, we're going to have 2 times 2 plus 8, which is going to be 4 plus 8, or 12. This is going to be 3 times 2 squared. 3 times 4 is also 12. So since the derivative is the same on both sides, I can include 2 on the interval. And I'm including it on the bottom one just because it was here, but it really doesn't matter which one because it's the same for both. Okay, so after all that, we know the mean value theorem applies because the function is continuous and differentiable on the interval. So I would want to leave this work on there, and I'm going to say mean value theorem applies because f of x is continuous and differentiable on, and I'm going to include the endpoints again because we know it's continuous and differentiable at the endpoints. Differentiability does not have to include the 1 and the 3, but in this problem it does, so just makes my writing a little bit easier. So now that I know the mean value theorem applies, I want to find the values where it works. So I'm going to clear my work here just so I have some space, and I want to do two things. I want to find the average rate of change over the interval. So I want to find f of 3 minus f of 1 over 3 minus 1. So f of 3 is going to use this one right here. We plug 3 in. That's going to be 27 plus 12 is 39. Minus f of 1, we're using the top here. 1 plus 8 is 9. And then on the bottom, we have 3 minus 1. So we have 30 over 2, which is 15. So the average rate of change, or the slope of the secant line, is going to be 15. What we want to do now is take the derivative, which we already have written down. So it's going to be 2x plus 8 for x values less than 2, and 3x squared for x values greater than or equal to 2. So I want to plug in c into the derivative and set these equal. The tricky thing here is I actually have to do this with both of them because I could get a value from c from either branch. I know I have to get one from at least one of them, but I could get one from both. So I'm going to do this two different ways here. So I'm going to say 2c plus 8 is equal to 15. That's going to give us 2c equals 7 and c equals 7 halves. So I need to check a couple of things here. Since I'm using this branch right now, that value has to be less than 2 for it to work, and 7 halves is not, so I can throw it out right now. Even if I didn't throw it out because of that, I also have to make sure it's on this interval right here. So even though I get a c value here, there's two different reasons that I need to throw that out, because not only is it not on the branch, so it's not even on the function, but also it's not in the interval in question. We're also going to solve this equation, 3x squared equals 15. That gives us x squared equals 5 and x equals positive or negative square root of 5. So same thing, I want to make sure that I'm choosing a value here that is on this branch of the piecewise function and is on this interval. So the first obvious one that I can throw out is the negative square root of 5. So I can eliminate that. The positive square root of 5, hopefully that works because the mean value theorem says we have to have at least one answer. Remember, the square root of 5 is a little bit bigger than the square root of 4, and the square root of 4 is 2. So this is greater than 2. However, it is less than 3, so it is on this branch of the function. It's also less than 3, so it's on this interval, which means that that is going to be our value. So I should have had c's in here. Sorry, 3c squared, c squared, c. So our answer here is going to be c equals square root of 5.